Today we're going to continue our look at sequencing series and power series, known as chapter 9 in the book. Specifically, we started looking at whether a series converges or not. We need to find a way, just by looking at it, to determine if a series converges or diverges. One of the main reasons that we care about whether a series converges or diverges is that the series is an output for a power series. We want to figure out what we can plug into a power series and get a convergent series. So we need to be able to look at a series and decide quickly if the series converges or diverges. If you would recall, we just got to keep track of what we've determined about convergence of series. So the first thing we had was our brute force, which was a sequence of partial sums. If the sequence of partial sums converges, then the series converges. Moreover, the limit of the sequence of partial sums will be the sum of the series. Here we're just looking at the total after we add the next term and see if that's headed anywhere. Next, we have the test for divergence. If the limit of the terms is not 0, then the series diverges. So what this means is that we have a numerical, although numerically intensive, computationally intensive approach, and now we can just look at the sequence of partial sums. You ask the computer to come up with the bunch of terms for the sequence of partial sums, tell me what the high ones are, and then we can look at those numbers and decide if they're approaching some limit. One way we can quickly tell by inspection is if the limit of the term is not 0, then the series diverges. One of the things that we want to keep separate, we're mixing our limits, our convergence for a sequence of partial sums, that's the sequence, and the convergence for our series. Remember that convergence means different things depending on what we're talking about. When we're talking about a sum, the series, or sorry, when we're talking about a series, the series converges if the sum is finite. But for a sequence converges if the terms have a limit. So when we're looking at the sequence of partial sums, we're just looking for it to see if that sequence has a limit. But we're trying to determine if the sum is finite. Then yesterday, we had a few examples. We had the series 1 over n called the harmonic series. This is our first example of a series where the limit of the terms is 0, but the series diverges. The limit of the terms is 0, and the series still diverges. This is interesting because this series diverges despite the fact that the limit of the terms is 0. Even though in the long run, we're adding an amount to the sequence, to the next term of the sequence partial sums that is very close to 0, we're still adding enough that the sequence continues to increase. We're still adding enough. Even though what we're adding is close to 0, it isn't close enough to 0. One of the ways that we saw this, we are in the middle of sawing this, is to consider the improper integral . What we found was that this improper integral diverges, and we want to use that to show that the series diverges. So we consider the improper integral from 1 to infinity of 1 over x to x. So to think about the area that this improper integral represents, we have the area under the curve 1 over x starting at 1 and going to infinity. So we can read since the improper integral goes to infinity, we can read that as the area going to infinity. So the improper integral diverge because the limit of the improper integral is infinity. What we want to notice, so we can interpret this as the area. So we're thinking of this as telling us that the area is infinite. What we want to notice is that the harmonic series is an overestimation of this area. So the harmonic series, the first term is 1. The harmonic series is an overestimate of the area. There's going to be a left endpoint approximation of the area under 1 over x from 1 to infinity with the delta x of 1. So here's that first area of 1. And then the next area is 1/2. And then the next area is 1/3. And so on. So the harmonic series is an overestimate of this area. Therefore, since the area is infinite, the harmonic series must also be infinite. Since the improper integral diverges, the series diverges. So this highlights an important technique that we can use. We can look at our series and analyze it using an improper integral. This is called the integral test. So we're going to make a function out of the terms of our series. Notice I'm not saying that function is the sum. The series is the whole thing. I'm just looking at the x term. If the improper integral converges, oops, it's not the one that we use, but it's the one that I'm about to say anyway. If the improper integral converges, then the series converges. If the improper integral diverges, then the series diverges. So this is great news. If you want to determine if a series is convergent, all we have to do is look at the improper integral and integrate the function, integrate the terms of the series. This is horrible news. To find out if a series converges, we have to integrate the term of the series. This is good because it gives us something to do. It's bad because the thing that we have to do, we might not like, because we might have to integrate something. And we remember all the algebra that was involved in integrating rational functions. We do get an important result from the integral test. We don't really want to have this integral test because we really want to integrate stuff. I mean, I really want to integrate stuff, but I don't know about y'all. We get an important result from the integral test. An important result from the integral test is we get P series. So this is a series with a specific form. So far, we've been looking at series with AN, generic term. This one has a specific form. The series 1 over n to the p. The series 1 over n to the p converges if p is greater than 1 and diverges if p is less than 1. So we get this from the integral test. And if we just look at the improper integral, 1 over x to the p from 1 to infinity. So what we notice here is we're going to look at what happens as b goes to infinity of b to the negative p plus 1. Now we can see the values of p, which will have p in the denominator, or sorry, the x to the negative p in the denominator or in the numerator. When p is equal to 1, then we're not integrating this way. We get the natural log, that's the harmonic series. We already know that one diverges. So let's just rule that part out. Suppose p is not 1, so we can do this. Then we start doing our improper integral. Since p is not 1, we can add 1 to the exponent and divide by the new exponent. Dividing by the new exponent is not the relevant bit here. That's just a constant. We can't take a divergent series and make it converge by multiplying by a constant other than 0, which would be cheating. We also can't make a convergent series diverge just by multiplying by a constant. If we take a convergent series that represents a finite sum, if I multiply that by a constant, I still have a finite product. But here we can see what's going to happen to this x. This x is in the denominator if p is less than 1. If p is less than 1, sorry, I said the other way around because I looked at the divergence right away. X shows up in the denominator if p is greater than 1. If p is equal to 2, negative 2 plus 1, x is negative 1, that x is in the denominator. If p is less than 1, x ends up in the numerator. And then when b goes to infinity, b in the numerator goes to infinity. B in the denominator goes to 0. So based on this, you would say if p is greater than 1, then x ends up in the numerator. Denominator. If p is greater than 1, then the x will end up in the denominator. Then when it goes to infinity, this term will go to 0. If the other thing, p is less than 1, then x is in the numerator. If p is equal to 1, we already know the harmonic series diverges. So we can summarize that as an important result from the integral test. This is going to give us a series that we can look at and instantly decide if they converge or diverge. So the series 1 over n squared, converge or diverge. Here, p is equal to 2, so this one converges. We have p series and p is equal to 2. P is greater than 1. The series 1 over the square root of n, this one will diverge. And here, because p is equal to 1/2, which is less than 1. We have the series n cubed. This series diverges. Even though we could justify it by saying this is a p series with p equal to -3, which is less than 1, we would not want to do that, because then we're missing the big picture. The terms don't go to 0. So the justification over here is that the limit of the terms is not 0. But we could also justify it by saying there's a p series with p equal to -3, which is less than 1. But the primary thing we want to notice here is that the terms don't go to 0 for the series diverges. So what if I don't have an actual p series? What if I have something that is p series adjacent? So this is not, well, actually this one is, because it's just n minus 5. What would you guess happens with the series 1 over n minus 5? We know that the harmonic series diverges. If it was just 1 over n, then this series diverges. This is just 1 over n starting in a different place. This one diverges because it looks like a harmonic series. Then we just have to decide what we mean by looks like the harmonic series. So we suspect that this series diverges. And we're thinking it looks like a harmonic series. We look at the series 1 over n squared plus 5. We might think that this is a 1 over n squared. Maybe this one converges because it looks like this 1 over this p series. It's not a p series, but it's looking like a p series. We're suspicious and think this one probably converges. It looks like the series 1 over n squared is a convergent p series. In both these cases, we would be correct. The first one diverges, it's like a 1 over n. The second one converges, because it looks like a 1 over n squared. Neither one is a p series, but we are comparing them to a p series. And we're doing that because p series, it's really easy to determine if p series converges or diverges. So what if I have a series Now, before you copy this whole thing down, remember what we're doing here. We're looking at what happens is when n is very large. In this fraction, in the numerator, for large values of n, what's the most important term? The n squared is what matters in the numerator. When n is very large, when n is 1,000,000, this 7 doesn't mean much. This -8,000,000 doesn't mean much. This is 1,000,000 squared. This is a 10 to the 6th. This is a 10 to the 12th. This n squared does not care about this 8,000,000 over here. I don't know what the word is for 10 to the 12th. You see what I mean? Well, it doesn't matter. There's 10 to the 6th. And we think, wow, that seems like a lot. I'd like to have $1 million. Well, what if there's someone over here with a 10 to the 12th dollar? Take it from them, they won't even notice. So for large values of n, the important term in the numerator is 9n squared. That's the only term that matters. In the denominator, the only term that matters is this 6n cubed. Because now this 6n cubed doesn't care about even that 1,000,000 squared. 10 to the 6th is nothing compared to a 10 to the 12th. And over here, we've got 10 to the 18th. That doesn't care about a 10 to the 12th. So all we really care about is the numerator, the biggest term in the numerator, and the biggest term in the denominator. Now we just blur our eyes a little bit even more. So we're just taking the focus and looking at this, just reducing the focus on this fraction to see what really matters. And then we reduce the focus even more, because when n is extraordinarily large, the 9 and the 6, those will just all even out. We're just worried about what's going on with the 1 over n part. We're not going to multiply by a constant and make a divergent series converge, nor are we going to multiply by a constant and make a convergent series diverge. That's how insignificant finite values are compared to infinity. So when we look at this series, when we blur our eyes, try to look at one of those 3D pictures where you relax your eyes and just kind of see the whole thing. I can't do that because I see 2 of everything already. So if we just look at what's important here, this is going to be like a 1 over n. So we're going to suspect this diverges. Let's say this looks like the harmonic series. Just focus on what's important. Is an n squared over an n cubed? And for large values of n, the 9 and the 6 are only going to matter if n's are about the same. So the 9 and the 6 only really matter when n is about the same. The 9 and the 6 are only useful for comparison when the n's are the same. If these are both n squareds, for example, then it's like a 900 over a 600. Now the 9 and the 6 matter. One person says, I have $900. Another person says, I got $600. That's comparable. The 9 and the 6 are useful. But in this n squared over n cubed, the person in the numerator, I got $9 million. The person in the denominator says, that's cute. The 9 doesn't matter because it's only in millions. The n, oh, if I switch to millions for n squared, what's that? 10 to the third cube, 10 to the 9th. At least I have words for that one. If n squared represents a million, n cubed represents a billion. And if you've got $6 billion, if someone, it doesn't matter what number someone says before the word millions, you don't care. 9 million. Bleh. Who cares? We have 6 billion. You only care about the word in front of millions until it starts getting close to 1,000. Then you start worrying about the 6 in front of your billion. That makes sense? How's everybody okay? That's funny because you see, you used to be able to refer to millionaires as wealthy people, and those two words were just the same. Ah, that person is a millionaire, and it's like, oh, how fancy. But now someone would be like, oh, that person is a millionaire. It's like, oh man, so they still can't buy in the Bay Area. You know what I mean? It just doesn't matter. It's the power that determines. And then once we get down to the ratio of the constants, that only matters when the degrees are the same. If it's a billionaire fight, they're both n cubed, then it's like, well, I have $9 billion. Then the other one has, I only have $6 billion. But then they realize that they're both billionaires. They high five each other and say, let's go exploit some more poor people. That's the only way, billionaires. We see you. You only got there because you're a bad person. Someday we're going to realize that. You know what I mean? All right. So the integral test seems daunting because we have to integrate stuff to find out if it converges or diverges. But the integral test hands on to us the P series. And with the P series, we can start looking at the comparison tests. But that will be for next time. And what we're going to be doing with the comparison tests is quantifying what we mean by this looks like, the harmonic series. Looks like the series one. Why do I have looks like? Let's make a bold L. There we go. We need to quantify what this looks like means, but apparently we're not going to be doing that for another week. All right, so that's it for today. That's it for this week. Everybody have a good spring break, and I'll see you on the following Monday.